Hello Bobcats. So in this video we're going to talk about ionic compound nomenclature, and to be more specific, binary ionic compounds. So today will be more about, or this video will be more about binary ionic compounds. But first let us talk about how do you recognize that you are looking at an ionic compound when you see a formula written down. So ionic compounds are metals. It's a metal bonded to a nonmetal. So 99% of the time it'll be a metal. I will later on in this lecture give you an instant when it would not be a metal, but 99% of the time it's a metal to a nonmetal. It is always a cation bonded to an anion, or positive bonded to a negative charge. So we have, and the cation is always written first in the compound, and the anion is always written second in the compound formula. Okay? So that's how we recognize that we're looking at ionic compounds. It's a metal to nonmetal, or a positive charge bonded to a negative charge. It's a cation to anion, and it's always the positive or cations first, and the anion is written second. So let's specifically look at binary ionic compounds. There's binary and ternary, but we're going to look at binary in this video. I'm having a hard time spelling my words today. Okay, binary ionic compounds. Now, binary ionic compounds are made of two types. That's why it's binary. Two types of elements. So an example would be, let's say, calcium chloride. Now I know there are three atoms here, two chlorines and one calcium, but there are two types of elements, calcium and chlorine. So there's two types of elements. And these are made of what are called monoatomic ions. Mono meaning one, so one atom, monoatomic ions. Single atom ions. And so we have a couple of different ones. We have cations. So let's look at cations, the monoatomic cations. And again, they're going to be the metals, which would be like sodium 1+, or lithium 1+, let's say magnesium 2+, iron 3+, and so forth. These are single elements making an ion, and they're cations, they're positive ions, and they're single elements making them. So we have the cations, monoatomic ions, and then we have the anion monoatomic ions. So anions are like nitrogen 3-, or oxygen 2-, or chlorine 1-, etc. So again, it's a single element making the negative charge. Now, where do we know, how do you determine what the charges are on your monoatomic ions? So we're going to look at a periodic table for right now and discuss how we determine charges on the periodic table. So if you look at this, group 1, these metals will always be a 1+. They have one valence electron, or one electron in the outer energy level. They will lose that electron to have a filled valence energy level, a field energy level of 8. So like, well, I won't go there. We'll talk about that later. Everything in this group is going to be a 2+, because they have two valence electrons to lose. And then these are the transition metals. Now transition metals can change charge. It's one of the reasons they're called transition. They'll transition from one charge to another. In this case, like iron can be a 3+ or 2+. Nickel can be a 1+ or 2+. Cobalt can be a 1+ or 2+. Manganese can be 2+ or 3+. And the way we determine those charges is based on the anion, and I'll show you how to do that later. However, there are three transition metals that have charges that don't transition. Zinc will always be a 2+, silver would always be a 1+, and cadmium will always be a 2+. Then in this group over here, we're going to have a 3+. They had 3 valence electrons to lose. But we need to be aware that the boron is most likely not going to lose electrons. They will share, because remember, the electrons are lost by metals, and the metals are everything below this zigzag line. And so a boron is I know it's a metalloid, but it behaves more like a non-metal. So it tends to share electrons. But aluminum will lose 3, so aluminum will be 3+, gallium will be 3+, all these metals will be 3+. Here we have a 4+ or minus. Now again, the carbon and silicon tend to share electrons rather than gain or lose. This is a metalloid and this is a non-metal. But once we get below this line and they're metals, they will be charged with a 4+. However, we need to be careful. Tin and lead can be a 2+ or a 4+, and lead can be a 2+ or a 4+, and we'll learn about why later. Then we hit this side. We've got nonmetals, so we're going to 3-. In other words, nitrogen has 5 valence electrons. It'll gain 3 to get to 8. Or you can say that it will gain 3 so that it will have the same number of valence electrons as neon, or a filled energy level. Remember, the noble gases have filled energy levels. So it'll go from 7, it'll gain 3 to get 10. It's not neon, it just has 10 electrons. Until you get to the metals, and then again, once you get below this line, they do not gain electrons, they lose electrons because they're metals, so they'll be 3+ and 3+. Here, 2-, all the way down. We don't worry about polonium because anything higher than number 84 is radioactive, and we do not use radioactive elements in general chemistry. It's a nuclear chemistry problem. And then these are 1- and these are 0. So, and all of these are 1-. And so these are the charges, and how you find the charges. Except for the transition metals, we will have to determine those charges from the anion that they are bonded to. Again, 1+, 2+, 3+, 4+, but we look down here, tin lead is 2+ or 4+. Then we have 3- because they're going to gain electrons until it becomes a metal. Then they're going to lose electrons. They become 3+. Here we're going to gain 2 electrons, and then we're going to gain 1 electron. So 2-, 1-, and 0. So that's how we know where the charges are located, or how to determine charges. Next, when writing the formulas, for binary ionic compounds, the charges must result in a neutral compound. Okay, and that's how we determine the number of atoms in that compound. So here we'll say that the charges determine the number of atoms in the compound. Now the reason I say that is because students will make a mistake in that if we look back up here, they'll want to say calcium dichloride. They want to use a prefix to indicate the number of chlorine atoms here, but we do not, again I will repeat, we do not use prefixes for ionic compounds because it is the charge that determines how many atoms. So we do not need a prefix to tell us how many atoms there are in an ionic compound. Now let's go through a couple examples. So let's say I have a potassium, and potassium's group 1, so it's a 1 plus, and oxygen, which is in group 16, so it'll be a 2 minus. Now what we have to here, we have a 1 plus and a 2 minus, so that is not neutral when they combine. But in order to combine to get neutral, we really need 2 potassium 1 pluses. Because now I have a 2 plus and a 2 minus, that will be neutral. So when I write this, I would write it as K2O. The subscript tells me how many of these atoms I need. So I need 2 potassiums and 1 oxygen. When I look at it, again, the logic is that I have 2 times 1 plus, so that's a 2 plus, 1 times 2 minus, 2 minus, 2 plus and 2 minus makes 0 or neutral. Let's look at another one. So if I take magnesium, and magnesium is a 2 plus, and nitrogen, which is a 3 minus, I see here that this, to get a neutral charge, I need a common denominator, and so a common denominator between these two would be 6. So in order to get a 6 plus, I need 3 magnesiums, because 3 times 2 plus is 6 plus, and in order to get a 6 minus, I need 2 nitrogens to get a 6 minus. So I would write it as Mg3N2. So, and I look at it again, and the reasoning is 3 times 2 plus is a 6 plus. 2 times 3 minus is a 6 minus. So that gives me a 6 plus and a 6 minus. That's a neutral compound. Now another way we can look at this is we can use what's called the Crisscross Method. And all you do is you take the value, not the charge, but the value, and put it as the subscript of the opposite element. And so that 3 would go with the magnesium, and this 2 would go with the nitrogen. And you'll notice that I have a 3 and a 2, and so it will work. If I looked over here and did it, I could have done it this way too. I could say, well, that 1 goes with the oxygen, that 2 goes with the potassium, and so K2O. We don't write 1 because when you write the element, it's understood as 1. Now, you have to be aware, though, that there's sometimes that this doesn't really work, and that would be, for an example, if I have aluminum, that is a 3 plus charge, and a phosphorus, that is a 3 minus. Well, we already know that's a 1-to-1 ratio. That becomes neutral. So all I would have to do is write ALP, aluminum phosphide. However, let's say you are in the habit of doing the crisscross and you did it automatically. Let's look. You can still do this, but what you have to be aware of is that when you write this down, this is going to be written as Al3P3, but there's a rule. Remember the rule that all ionic compounds have to be written in the lowest whole number ratio. This is the lowest whole number ratio here. This is the lowest whole number ratio here. I cannot reduce it anymore. But if I divide by 3, I can actually reduce this to ALP. And so don't forget, if you do the crisscross, make sure you have reduced it. But I'm going to cross through this to show you that that's not the correct answer. The correct answer is ALP, a 1-to-1 ratio. Now, let's look at how we would name binary ionic compounds. So the next thing is naming binary ionic compounds. So naming. So first, all we need to worry about here is that cations, if we look at each ion and see how the ions are named, then we just write the names of the ions. So cations use the name of the element. So cations, you just use the name of element. So for example, let's say I have Al3+. That's an aluminum ion. So we just write aluminum ion. Or if I have, let's say I have Na1+, that is sodium. So, and it's an ion, so we'd write sodium ion. So you just use the name of the element and write ion if it's an ion. Now what about the anions? The anions have a different rule. So let's look at anions. Now anions use the root of element name ending with "ide." So use root of element name ending with IDE, ide. Okay, so let's look at what we mean by this. So I have oxygen 2-, so the root would be ox, so that would be oxide. I end it in ide. Or if I have N3-, that would be nitrogen or nitride. Nitride, this is the root, ide. Or if I have P3-, that's phosphide. Now in these cases, you don't say nitrogenide or phosphoride, you just say nitride, phosphide. Again, if I have S2-, this would be not sulfuride, but sulfide ion. Oh, forgot the word ion, so it's ion, ion, ion. And last, we'll look at Cl1-, this would be chloride ion. Okay, so those are the names of the ions. So then we just take the name of each ion and write it to name the compound. So for example, if I have CaCl2, I would write that. I've got a calcium ion and a chloride ion, so that would be calcium chloride. Or let's say I have, let's go back to this one, Mg3N2, I had a magnesium ion and a nitride ion, and so that would be magnesium nitride. So a couple of examples. Let's look at a couple examples from names. So if I have, let's say I have potassium sulfide. So to write the formula from the name, I would just say, okay, potassium is K1+, sulfide, if it ends in ide, that means it's an anion, so that would be an S2-. Now I'm not going to show the crisscross, but I'm just going to do it and say, okay, this 2 means that I need 2 potassiums, and this 1 means I need 1 sulfur. So that'd be K2S, potassium sulfide. Or let's say I have aluminum oxide. Okay, so I write down the aluminum ion, that's Al3+, the oxygen ion or oxide ion, O2-. Do the crisscross, so this 3 means I need 3 oxygens, this 2 means I need 2 aluminums, so it'll be Al2O3. 3. And that we will finish this video with those 2 examples. There are several practice sheets if you need so on my resource page. And have a good day.